Hey everyone, welcome to Motion Equations Podcast. I'm Aisha, and today we're diving deep into one of the most fascinating topics in physics, projectile motion. Whether it's a basketball soaring through the air or a cannon firing across a battlefield, projectile motion is everywhere.
That's right, Aisha. I'm Marcus, and I'm excited to break down how kinematic equations help us predict exactly where and when a projectile will land. The key to understanding projectile motion is recognizing that it's really two separate motions happening at the same time.
Exactly. Let's start with the basics. When we launch a projectile, we need to think about its motion in two directions, horizontal and vertical. The horizontal component and vertical component are independent of each other, which makes our calculations much simpler.
That's the crucial insight. In the horizontal direction, there's no acceleration acting on the projectile, assuming we ignore air resistance. This means the horizontal velocity remains constant throughout the flight. We can express horizontal displacement using the equation x equals v naught x times t, where v naught x is the initial horizontal velocity and t is time.
Perfect explanation, Marcus. Now the vertical direction is completely different. Gravity is constantly pulling the projectile downward with an acceleration of approximately 9.8 meters per second squared. This is where our kinematic equations become essential. The vertical displacement follows the equation y equals v0 times t minus 1/2 times gt squared, where v0, y, is the initial vertical velocity and g is gravitational acceleration.
And here's something really important. The vertical velocity changes over time due to gravity. We can find the vertical velocity at any moment using v(y) equals v0(y) minus gt. This shows how gravity continuously affects the vertical component while the horizontal component stays constant.
Let's consider a specific scenario. A horizontal launch where the projectile is fired parallel to the ground. In this case, the initial vertical velocity is 0. So v naught y equals 0. This simplifies our vertical displacement equation to y equals -1/2 times g times t squared. The negative sign indicates downward motion.
Great example. For horizontal launches, we can find the time of flight by solving for t when the projectile hits the ground. If the projectile starts at height h, then h equals 1/2 times g times t squared, which gives us t equals the square root of 2hg. This tells us how long the projectile stays in the air.
Once we know the time of flight, finding the horizontal range is straightforward. Since horizontal velocity is constant, the range r equals the initial horizontal velocity multiplied by the time of flight. R equals v naught x times the square root of 2hg. This equation is incredibly useful for predicting where a horizontally launched projectile will land.
Now let's tackle the more complex scenario, a general launch angle. When a projectile is launched at an angle theta above the horizontal, we need to decompose the initial velocity into components. The initial horizontal velocity is v naught x equals v naught times cosine theta, and the initial vertical velocity is v naught y equals v naught times sin theta.
This decomposition is powerful because it lets us use the same kinematic equations we already know. For a launch and landing at the same elevation, the time of flight becomes t equals 2 times v naught times sine theta divided by g. Notice how the angle directly affects how long the projectile stays airborne.
And the horizontal range for equal elevations is given by r equals v squared times sine 2 theta divided by g. This equation reveals something fascinating. The maximum range occurs at a 45-degree angle. At this angle, sine 2 theta equals its maximum value of 1.
That's a beautiful result from mathematics and physics working together. Let me emphasize the key kinematic equations we use for projectile motion. For horizontal motion, x equals v0 x times t. For vertical motion, y equals v0 y times t minus 1/2 gt squared, and vy equals v0 y minus gt. These three equations are your toolkit for solving virtually any projectile motion problem.
Students should also remember that these equations assume constant acceleration, which is valid when air resistance is negligible. In real-world scenarios, air resistance does play a role, but for most introductory physics problems, we can safely ignore it and use these elegant equations.
Let's work through a quick example to tie everything together. Imagine a ball is launched horizontally from a 20-meter cliff with an initial velocity of 15 meters per second. First, we find the time of flight. T equals square root of 2 times 20 over 9.8, approximately 2.02 seconds. Then, the horizontal range is r equals 15 times 2.02, approximately 30.3 meters.
Excellent walkthrough, Aisha. And if we wanted to find the vertical velocity when the ball hits the ground, we'd use Vy equals 0 minus 9.8 times 2.02, approximately negative 19.8 meters per second. The negative sign indicates downward direction. The total velocity at impact would combine both components using the Pythagorean theorem.
Understanding these components is crucial because it shows how projectile motion isn't mysterious. It's just two simple motions combined. The horizontal motion is uniform, and the vertical motion is uniformly accelerated. When you master these kinematic equations, you can predict the trajectory of any projectile.
As you practice these problems, remember to always identify your known variables, choose the appropriate kinematic equation, and solve systematically. Draw diagrams showing the horizontal and vertical components separately. It really helps visualize what's happening.
Thanks for joining us on Motion Equations Podcast. We've explored how kinematic equations break down projectile motion into manageable horizontal and vertical components. Whether it's a zero launch angle or a general angle, these equations are your foundation for success in physics.
Keep practicing, stay curious, and remember, projectile motion is just physics in action. Until next time, this is Marcus, reminding you that understanding motion equations opens up a whole new way of seeing the world around you. Thanks for listening.